maybe you had. Again, everybody covers concentrations differently in Gen Chem 1 and 2, but those are where those topics are introduced. We're going to learn to use them throughout the semester here, so we'll just continue on that road. Okay, so we're going to continue in the notes today, finish up Chapter 1, roll right into Chapter 3, and try to get all some things to look at going into your 3-day weekend. So, last thing we looked at was this stoichiometric conversions, where you're looking at relationships and problems, where you take a mass. And kind of a key thing that I like to try to emphasize what we're trying to accomplish in these things is what's the strategy or the setup. So we went from mass, I want to write there, mass to moles, and of course we do that conversion with a molar mass of something, and then we use the stoichiometric factor to go to moles of one material, so from moles of X to moles of Y. It looks like an X, Y. And then we went back to mass in this one. And finally, we've got mass of the material, and we could use that to calculate our percent mass. That's kind of the strategy that we used on that problem. The thing I encourage you when you're working these gravimetric problems like this, have a game plan. Try to figure out how and sometimes the game plan is start with the end. Okay, so if I look at this problem and what I've got in red, what I need to do is calculate the percent weight. That's the first thing mentally I want to figure out. What do I need to do to find that? Well, mass of the sample is given. That's no problem. So I've got to go backwards from that then. Well, I've got to find mass of the iron. How am I going to find mass of the iron? And that's where you set up your procedure to go through that. Okay, so I think where we were at now was y'all's turn to work on these problems. So this is how airbags work. Airbags contain a highly reactive compound called sodium azide, and it decomposes, produces some sodium solid. More importantly, it produces nitrogen gas, which very rapidly expands. And since it's unimolecular, there's no limiting reagent. It's only one component. So I want to know how many grams of nitrogen gas are made if a certain mass of the reacting reagent reacts. Well, it's not, I don't know who it is. He's not setting value that usually is. Okay. And he was gone somewhere today, he said. Got half of you. A few more.
My cat pain this morning, so I just kind of stared at the board for about a minute before I was like, oh, this is mad.
Last two. Last one. All right. Again, as everybody says. Most of you says choice A. Being choice A. Okay, I'm not going to go through the whole thing completely, but I will quickly show you for the couple that didn't get it how to set it up. All right, so we know a reagent. We've got 6 grams of sodium azide. First thing I want to do is go from mass to moles of it. Sodium azide is 65.011 grams per mole. Sodium azide. And now, what's the key thing I have to put in here? Stoichiometric relationship. So those of you who missed it, it's likely where you missed it. So I need to look at the balance reaction which is given, and I need to know the mole ratio between the sodium azide and the nitrogen gas. 2 moles of sodium azide to 3 moles of nitrogen gas. Now that gives me moles of sodium azide, or of nitrogen gas. 1 mole of nitrogen gas weighs 28. It's looking for grams of N2. If I just do my dimensional analysis, see if I've got things set up right, grams of sodium azide cancel out, moles of sodium azide cancel out, moles of nitrogen cancel out. .88 grams. Okay. It's typical of the types of calculations that we're going to be doing. We're going to be applying these to equilibriums, to titrations, to everything else, but we're going to be, sometimes we come up with the moles with a mass, okay? Sometimes we come up with the number of moles. What we're going to do in the lab so much is concentration times volume. This is how we're going to find our number of moles. But we're going to go through a similar type of conversion. All right, and we're going to determine an amount of something, a concentration of something. This is the type of things that you need to do pretty routinely. Okay, I didn't go back and look, and I remember I added this problem last year. Did I work it in the video last year? Y'all seen this problem? I don't think it was in the video. Okay, so I thought it. I didn't think I had. I added this as an extra one to work. So this is another one of these types of problems that we have to look at a relationship. So you've got this is an example of a gravimetric analysis. So you've got an alloy that's made out of 2 different things. So this is platinum and iron and fillings. And we've got a massive sample. And we ignite the sample in the presence of air. So that means oxygen. And the mass increases by a certain mass. Okay, now it wants us to go back and find out what's the percentage of platinum in the original sample. So this one would require some knowledge of what's going to happen with some chemistry. So what can you tell me about platinum and iron in terms of metals?
Platinum's unreacted.
It's inert. Platinum's one of the most, it's like gold, it's one of the most unreacted metals. And we know iron will react with oxygen and it will produce iron oxide. So the reaction that's going to occur is the platinum is going to remain platinum, but what's going to happen with the iron? The iron's going to react with oxygen in the air, and it's going to produce Fe2O3. It's going to go to iron oxide. Oops. Let's try that again. Fe2O3. Okay, so what we can look at is the increase of mass, and we know the increase in mass is purely due to the oxygen. So we can take the change in mass, the delta mass is from increase oxygen. We can take the mass of the oxygen, and just think the strategy out with you, relate it to moles of oxygen, and then finally moles of FeO2, Fe2O3, and finally moles of Fe, and ultimately we can get to the mass of Fe. And the question asks, what's the weight percent of the platinum? But we're going to have to get there the back way. We're going to find the weight percent of the iron and subtract to get the platinum. So that's kind of the strategy that this problem works. This was a final exam question a couple of years back. So one of the old retired ACSS. This is the general knowledge for gravimetric analysis that they expect you to do. Okay, so this is the reason I plucked this question out. Okay, so let's look at our strategy doing it. So let's get find the delta mass. I'm going to take the two masses and subtract them from one another. Play along in your calculator if you got it. Make sure I don't enter something wrong, because I'm just as prone to it as you are. All right, so I got 0.7262 grams of oxygen. Okay, so now I'm going to take the grams of oxygen. There are 16 grams of oxygen for 1 mole of oxygen. Okay, now I can go, there are 3 moles of oxygen per 1 mole. I know I want to write, my brain's not making that happen today. 1 mole of, this is Fe2O3. So 1 mole of Fe2O3. Now I can relate that back to moles of iron. For 1 mole of, I'm just struggling today, guys. Maybe I needed your caffeine. I had 2 Diet Cokes. That's probably my problem. I'm in caffeine overload. There we go. 2 moles of iron. Now we can get to moles of iron. 1 mole of iron weighs 55.85 grams. We get that from the periodic table. Okay, so let's go ahead and find out the mass of the iron here. So, well, before I do calculations, I always like to convince myself I've got the units set up right. Moles of iron cancel out. Moles of iron oxide cancel out. Moles of oxygen cancel out. This is grams of oxygen. Grams of oxygen cancel out. So grams of iron, I think I got it right. Okay, so 2 times 5 by 16 divided by 3. Okay, I got 1.69. Anybody else get that? Okay, good. 1.689 insignificant 2. Okay, so define the percent Fe, which is the strategy I'm going to use. And here it wouldn't matter which way you did it. You could have subtracted from the mass of the sample. We know the mass of the sample, you could have directly got the percent of platinum, or the mass of the platinum. But I'm going to do it, find the percent Fe, and I know the other percent of it is platinum, but I'm going to do it with the mass of Fe divided by the mass of the sample, times 100. And the sample weighed 1 times 100. Those are both grams.
You take the actual mass.
Take what now?
Yeah, you divide it by
So I took the mass of the FE divided by the mass of the sample. And it's 60.72% iron. And I know the pieces have to equal the whole. So that means the balance of it has to be in platinum. So that means it's 39.78 or 28% platinum. And we probably quit using platinums for fillings because platinum has been very, very expensive.
Why did you take the initial?
We're at
The
here because this is the alloy by itself that just has the two components.
Okay.
That's before we burn it.
All,
See what?
the next one has all three.
That's correct. It has the oxygen come out of it. And what we want to know, what's the original sample? That's the key word at the end. Okay. And again, I think probably there was a much greater emphasis on gravimetric analysis like this going back 30 years ago. Today we do so many different types of analysis with instrumentation. The process of ignition and determining a composition is a slow process. Now, this is something you would burn for 24 hours in a blast furnace. We just don't do this type of analysis that much anymore. It can be fairly accurate, but it's extremely time consuming and it's prone to error because there's such a chance to spill a sample. If the oxygen's too aggressive blowing across the furnace, you can disturb the sample and blow some out the other side. It's just not used that much. However, the authors of these tests think it's knowledge that you need to know. So I'm not going to cover it as much in class. All right, here was the last thing that was in the notes, and I went over this in class, but or in the videos. But just to remind yourself how you do limiting reagents. Okay, so in this example, there was two components that A and B that were consumed. They're not consumed in an equal ratio because there's two of B's consumed for every one of A. And I said you've got some of A and some of B react, and I want to know what's the limiting reagent and how much is left over. So kind of the strategy that you use is find out which one. The strategy we taught from freshman chem was to convert both of these into moles of product and then find out which one makes the fewest amount of product. As you get to understand chemistry more, you should be able to look at this in your head and say, okay, I know, look at this number, and I'm looking at twice as much as this number, more than twice as much as this one, and it's not. So that tells me I'm going to run out of B first. Okay, and that comes with your comfort and your experience to go then knowing that was the limiting reagent. I can find out how much of A is left over. And we looked at that example in the video. Okay, so that is the end of this chapter. So that's chapter 1. So rolling right along into the next one. Chapter 2 is over things that we do in the lab. And I encourage you to look at chapter 2 as you're writing up your first report, because it has a very good description of what the capabilities of the instruments are that you use in the lab. It explains how things like the electronic balances work in great detail. It also gives you a lot of the limitations of the burettes, common errors, limitations of the pipettes, etc. Okay, the outline I've already went over, so again, I'm not trying to hammer you with problems, but at least try to look at that group of problems before we do the exam. Some of the things that we're going to do on this, I'll just emphasize now. We're doing some examples of it in class, but for a large part of it, you've got some personal responsibility to learn how to do these things. The terms on significant figures is just something we have to hammer into ourselves and do correctly. Okay, I'm going to hold you to what we learned significant figures from the rest of the year. So once we go over this chapter from now on, in my rule of significant figures, I'll tell you on a test, what I want you to avoid doing is writing down what the calculator spits out. Once you realize, and that's what this data chapter is talking about, that there's value in our data based on the numbers of decimal places or significant figures that we represent. So this chapter, when we do this section on the test, I'll give you some specific problems that are, give me the correct number of significant figures. And it may be a multiple choice problem, but on that problem, you're going to answer it exactly. Past that, everything else, I say I'll give you a 1 plus or minus 1 significant figure tolerance. So when you do your problems and your test questions are worth typically 5, 6, or 7 points, depending on the complication of the question. If you, the term I use is slaughter the significant figures. If you're not within plus or minus 1, I'd love for you to get it perfect. But if you're not plus or minus 1 significant figures, you'll get an SF minus 1. Significant figures minus 1. So if it's a 6-point problem, you may lose 1 point because you've missed the significant figures 2 digits or more. Okay? I just want to emphasize to you, and if you do that, if you don't pay attention to significant figures and you miss that on 8 problems, that's 8 points on the test. It adds up. Okay, so I want you to just learn how to do these things correctly going in, and you'll be on top.
We only use significant figures with our last answer, right? So we can use many decimals as one.
You can, absolutely. You can keep all the digits till you get to the end. Yeah. So, but when you report that final number is when it matters. But you have to be tracking them all the way through the calculation. That's what we'll learn. Okay, so I'm just trying to say who watched the videos. Okay, need a few more seconds. All right, that's all it is. Okay, most of you said it was choice C. That indeed is our correct answer. So high precision means grouping of the data. That's exactly what we have in this case. Here we're a shooter or whatever we are, but we have a good grouping of the data. However, we're missing the target. So we have high precision. The fact that we're missing the target, we're low accuracy. And this is the problem child data in the lab. Because our instinct is when we get data that groups very well, we inherently think it has good quality associated. And sometimes that's just not the case. Sometimes when we have problems, it's obvious that we have an error. And this was the one we went over in the videos. If you have a male that's pregnant, it's pretty unlikely. Sometimes we have errors that are easier to see. How the train fell off the second floor of the building, I don't know, but if you were around, that was an obvious error that had happened. So our problem is when they don't go so wrong and it's not so obvious to us. Okay, I'm going to quickly go over the significant figure rules with you, and then we're going to work on doing some applications of them. So you've had the opportunities to watch the videos to see how they go. So the emphasis is on the weakest link rule. So our calculations are limited by the answer that has the least number of significant figures in that component of the calculations. In this example, you multiplied something that has 6 significant figures, something in 3. The calculator spits this out, that we have to realize we have to round that to 3 significant figures because this is our weakest link in calculation. The thing we have to realize is that addition and subtraction are different from one another. Addition and subtraction are the same. Multiplication and division we treat differently. A key that we need to understand are conversions, like the metric system, are infinite precision. So there are exactly 100 centimeters in a meter. Infinite number of decimal places. So that never limits precision. Constants and integers are treated the same. So if there's a constant, we don't consider it limiting precision. Most commonly, we look at it limiting precision based on the data that's collected, whatever that data is. Okay? So all of these things we should be comfortable with, so you should know what are the significant digits. I went over these on the video. We're just going to quickly look at the review on this one. So this is the way we do with multiplication and division. So multiplication and division, it's the fewest number of significant figures, limits our answer. I've got a number with 3 sig figs, 5 sig figs, and 2 sig figs. My calculator spits out this. My weakest link is the 2 sig figs, therefore my answer has to be truncated to 2 sig figs. Okay? The division on the bottom, number with 4 sig figs, 3 sig figs. My calculator spits out this. My answer has to be truncated to 3 sig figs because that's the weakest link in multiplication and division. All right, addition and subtraction is a little bit different. What we do now, instead of counting sig figs, we count decimal places. Okay, so we go to our result can have no more decimal places than the measurement with the fewest decimal places. So here's an addition to start with. I've got 2 decimal places, 3 decimal places, 3 decimal places. This is what my calculator spits out. My weakest link's 2 decimal places. That's where my answer has to go. Okay. Now we get to a result like the bottom, and it's one that bothers us. We have 1 decimal place, 3 decimal places. I get this, and I realize I got to take it to 1. So it's only 0.8. And if we've collected a piece of data that has 4 significant figures in it, it just seems wrong to us to write an answer down with 1 significant figure. But that's the way we have to truncate it. Okay? It seems counterintuitive. You've done all this work to collect this good data, but if you've got a volume data involved in your calculation and it's only 1 decimal place, that's what you're limited to. Okay? So we just have to learn how to use that. Okay, so here's an example calculation. Let's go through these. So this one, I've got a couple of things. You'll run into problems like this. Spend a second. You try to work this. You got parentheses in there. I want you to come up with an answer, and then I'm going to work it. My guess is you're fixing to do a quicker problem. It's a pretty educated guess, too. Think about how you would report that to proper number of significant figures. Okay, I'm going to go ahead and start. We have to do what's the parentheses first. First thing I do is do my subtraction. What do I get when I subtract this? 9. No decimal places, just 9. Next thing is my multiplication. And I get 72.1512. So now I can multiply those together. And my calculator spits out 649.3608. And I think, wow, I've got some data here. Because I've got seven significant figures. How many significant figures should I have? 1. Weakest link, 1 sig fig, 5 sig figs, Okay? I've got 1 in this case. So, now, tell me how to report that correctly.
Would it be 600 under 50?
Would it be 600?
6 times 10 to the second.
Okay, so if I wrote 600, to me, I'm applying 3 significant figures in that. Okay? And if I write 600, and go back to a couple pages, I went over that in the video, that's, it's not clear. And now if I put a decimal place here, that is clearly 3 significant figures. But the problem with just writing 600, I don't know if I know it plus or minus 1, plus or minus 10, or plus or minus 100, which is what really I need to apply. Okay, so the way that somebody mentioned it, the way that we clearly represent it and the way that we want to do it is represent with scientific notation. That's the way we can clearly show the number of significant figures. Scientific notation. Okay? That's the practice we need to get into. All right. The thing I'll tell you is that leaving numbers like that, we just want to learn how to avoid them. They get us in trouble. All right. This one counts. More answers. Three more. Last 2. All right, roll in. Uh-oh. Well, we're 1, 4, and 5 on our votes. We don't have a clear answer. Let's see, what did we do? Interesting. Convince your neighbor you're right or wrong. Vote again. Talk it over. Some of you are right. Question is, who's right?
Well,
Okay, so it'd be like,
That's what I did, right?
Yeah, it was measured
it'd
out
be
to that.
point
Yeah, yeah.
three
Yeah, that's
five.
three significant figures, that's three significant figures.
I got the same
If you look at the,
But there's some, so this has,
subtraction,
this has 2 decimal places, right? And so when you subtract, you're supposed to go
or
by decimal places. So the
1.428
one that this is.
minus
That's fine.
1.0.
Yeah.
That's the point zero, right? No, you don't, because you look at decimal places and subtract, so you should only report 2 on the decimal place, so you have 2 significant figures. Because in subtraction, you look at decimal places, not the significant figures. Are we breaking that rule up, because there's 2 decimal places in that? So the question is the subtraction. You see that there's
So what they're saying
0.08,
is
so
this
you should
component
report your answer
only
with
has
2 decimals.
It's
So
limited.
0.34 or 0.35
What?
has 2 significant
Yeah.
figures.
Yeah. 0.35 instead of 0.05.
don't do it.
Okay, you're voting again.
I think, yeah, actually.
Maybe I can get at least one.
Yeah.
I'm thinking at least subtraction is what it goes down to.
Yeah. So I think it's the same. Yeah.
If you think you're right, win the argument. You don't have to agree with everybody else.
And then I'll figure out that.
Okay. Need 2 more votes. You're voting again.
Oh, I picked the wrong one.
You can vote again.
All right.
Yeah, it takes your last one, so you can,
Okay.
still need 1 more. Yeah, every time it goes dot, dot, check mark, that's the answer is recorded.
So it was
Oh.
1.02. Wait, yeah, you just typed it in a little bit wrong.
I don't know.
Because it's 0.36. You can 0.36.
Somebody take your guess at this point. We gotta go over this problem. All right, we're all in. Let's see. Some people stuck to their guns, so 70-30. C was the predominant choice. Let's see. Hope it wasn't B. Okay. Let's start working through the problem. Okay, so first thing I'll do is my subtraction. And my calculator spits out 0.348. But in subtraction, I'm going to underline my significant digit in each step. Okay, now I'm going to do what's inside of the parentheses on the other side. And my calculator spits out 3 significant figures, 3 significant figures. My answer is going to be truncated to 3. Okay, so now I'm going to do my division on the left-hand side again. And my calculator spits out. Okay, 1.208. Okay, so I'm doing division. How many significant figures on this guy? Weakest link's 2. Ah, crap. Okay. Okay, that's what my calculator spits out. In addition, it's the number of decimal places that are the limiting factor. On this case, I've got 2 decimal places, DP, versus 1 decimal place.
I had it right the first time. I changed that decimal places.
1, 2. Okay?
I had it right the first time, and then I chose it for some reason.
So we're looking at.
So we're going to do some problems like that. One of the things that I think you have an opportunity to explain to each other, and you learn that way, The thing I'll tell you on this is that if you know the answer, I don't care if everybody around tells you you're wrong. Go with what you think's right. Okay. The thing I'll encourage you to do when you get that second chance thing is figure out why they got a different answer than you did. It's peer-based learning, and I think it's a very powerful tool to use. And we'll use part of the class period to do that this year. Okay, those types of significant figures, y'all have all been exposed to some level. Okay, now maybe not in Gen Chem, it may not have been for strictly. I do, but you saw those things going back to high school. What you probably haven't seen a lot of were logs, significant figures with logs, and we'll use logs quite a bit this semester, both taking a log of a number and taking an anti-log in our calculations. So the rule is you keep the same number of significant figures in the number n that you're taking the log of is to the right of the decimal place in your answer. A stands for answer. So if you had X number of significant figures in whatever the original number is, so X sig figs, you have to apply the same number of significant figures to your answer. And when you take an anti-log, the same rule applies. Okay? So I went over a couple of examples in the notes, the ones down the bottom. You had this original number with 4 significant figures. That means you need 4 to the right of the decimal place when you take the log. And it works the same log base E or log base 10. We'll do mainly log base 10. In electrochemistry, we may do some log base E stuff. When you take an anti-log, you take to the right of the decimal place in the anti-log, and when you take the log of that, you go to the original number, to the right of the decimal place, 2 significant figures. Okay? What we need to realize when we take a log of something raised to a power is that this power is nothing but spacing zeros. It doesn't play a role. Okay, so here's a number. That number has 2 decimal places, but 3 significant figures. So to our answer to the right of the decimal place, we need 3 significant figures expressed to the right of the decimal place. Okay, so essentially a log, this is the scientific notation portion of it. So if you think about what a log does, this 10 to the 6 is all that's been expressed there. If it were 10 to the 5th, it'd be 5 something. 10 to the 4th, it'd be 4 point something. Okay, so that's all you're doing. That's your spacing zeros if you want to think about it. Okay, if you look at the one at the bottom, we need to count the number of significant figures that are in the what we're taking our anti-log of. Okay, so there are 4 in that one. So in our answer, we need to express our answer up to 4 because we're doing an anti-log now. Okay. We'll do some of those and get some practice and get better at it. So where we do these things a lot, and you'll learn in the upcoming chapters, you're going to be very, very proficient at taking pH calculations before the semester's over with. What's the pH of a strong acid? Well, the formula you use that, you learned in Gen Chem, pH is equal to negative log of the hydrogen ion concentration. In this case, my original data has the hydrogen ion concentration to 3 significant figures. So that means my answer goes to 3 significant figures. And the habit that we use, especially if we're going to use the calculation for something else, keep 1 insignificant figure in your calculations. Okay? And don't round that insignificant figure. Whatever it is, it is. All right? And usually that insignificant figure we represent as a subscript. Now, I'm not critical that if you don't include that subscript, I'm not don't care that it's absolutely there. The thing I'll tell you, if you have to use that number for something else in the calculation, in the long run, that keeping that insignificant digit will save you in a rounding error. Okay. And honestly, when you do a calculation, I'm not going to count off a rounding error for you. I know that it's easy to happen. The best thing that you can do is leave all the digits in the calculator and don't round to the very end. Okay, so
You underline your significant figures.
underline the following through so you can track them. And just, if everything's there, that's fine. So if you're writing it down, if I've got something that's got 2 or 3 digits in, I'm not going to write down everything on the calculator. So what I'm going to do is put the last digit and then the first insignificant digit as a subscript. That's the way I'm going to carry my calculations through. My calculator doesn't have, all of y'all that's got the newer ones, you can scroll back up to a previous number and use that number for calculation. My calculator doesn't have the ability to scroll up or anything. Okay, so I talked about this in the notes, so I'm going to very quickly go over this introduction. So one of the things that we have a problem with, and we have to just realize, same with our data that you collected, it's impossible to collect data that's totally free of error and uncertainties. What we have to do is try to minimize that error, and we have to estimate if it's an acceptable accuracy. That's going to be our goal. We're going to have to figure out how to do that over the course of the semester. So this was the example of the iron analysis, and the data is scattered from all the way down here at 19.4 all the way up here to almost 20.4. It's 3.5 or something like that. The average of those 6 data points is 19.78. The true value is 20, as it's determined to be in this one. So is that statistically bad data? Well, it depends on what's the acceptable of the accuracy. So if, for this particular analysis, if I needed a result plus or minus 100 of a part per million, which is the unit in this case, okay, if it had to be that accurate, then it was unacceptable. But if the window was plus or minus 25.25, which is still pretty accurate analysis when you consider how low a part per million is, it's wonderful data. Okay, it just depends on what you're trying to accomplish and the needs. So accuracy and precision, I went over those in the videos. One of the things that we have to just defeat ourselves against is that just like the one I showed you on the clicker question, assuming that you know something precisely doesn't mean you know anything about its accuracy. They're completely isolated things, and they're due to 2 different types of errors. The random error, it's also called the indeterminate error, it causes symmetrical scattering around the mean. And you cannot avoid this. It's going to happen. It's the minor imperfections of the world, okay, of your measuring equipment as you as the analyst and everything else. The other type of error, which causes a decrease in accuracy, is a systematic error. It causes the mean to deviate from the true value. And we just need to understand the difference in those 2 things. Now, whenever humans become involved, we have the potential for what's called a gross error, which leads to an outlier. That's when you have a point remarkably different from all of the other points in the set. Has anybody looked at their statistics yet, or looked at your typesetting or bureauing data? Is everything within 500ths? It's not. Anybody miss something about nil? Okay, that's a gross error. You read a burette wrong. Okay, and it happens. We just have to learn how to get in a habit to minimize or avoid that from happening. Okay? All right, that's going to be the point where we quit. So over the weekend, of course, we don't have class on Monday. Your lab report, you can submit it electronically, but if you're not going to be around a computer on Monday, I'll give you to Tuesday night and get it submitted. I'll change it. It says it's due on Monday night, but I'll switch it to Tuesday night. You need to go ahead and watch the rest of the videos in Chapter 3. Chapter 3 is a pretty short chapter as well. When we get through Chapter 4, we'll start slowing down a little bit. When Chapter 5, we're going to start kind of crawling because there's a lot of calculations. Okay? So, all right, y'all have a good Labor Day holiday.
So the lab we do Tuesday night.
Lab Day Tuesday night at midnight. Fix it, change that right now.
I didn't know how it,
Yeah.
I did it on Monday.
Yes.
Go to the library.